Hi, I'm Reece Coleman, Waterways and Wetlands Research Manager in the Applied Research team at Melbourne Water. And thanks for joining us for another edition of Melbourne Streams, where we're talking all things waterways and wetlands research. In this first series, we're releasing a talk a day based on topics voted on by the Waterways and Land crews. Today's talk is a special talk from Professor Tim Fletcher of the Melbourne Waterways Research to Practice Partnership with the University of Melbourne. Tim is the co-research director of the Melbourne Waterway Research to Practice Partnership and has expertise in stormwater quality, treatment and impacts, with research focusing on modelling stormwater flows, quantity and performance of novel stormwater treatment and harvesting systems. So I guess it's no surprise then that Tim's talk is about the fundamentals of stormwater management for waterway health. And this has got to be one of the best 30-minute summaries of the impacts of stormwater and what we can do about it for waterways that I think I've ever seen. So Tim starts by talking about how stormwater impacts waterways, such as flow, water quality, channel form, and aquatic life. He then talks about management principles and finishes with the various technologies that we can use as managers to try and deal with stormwater issues. If you have any technical questions about Tim's talk, then feel free to contact him directly. He's kindly provided his contact details. Or if you have broader questions about the Melbourne Waterway Research to Practice Partnership or the Waterways and Wetlands Research Program in general, then please contact either myself or Slobodanka Stojkovic, who's also in the Waterways and Wetlands Research team. And now, of course, you can search Research Hub on the intranet. So if you look for Research Hub, there you will find summaries of our research projects from the past 10 years or so, and also links to the various papers and reports and presentations coming out of that research. I really hope you enjoy Tim's presentation today, which has even a little section on how we might think about kebabs that fall on the street and what that might mean for waterway health. So we hope you enjoy Tim's talk, and we look forward to providing more in the days to come. Thanks.
Hello, my name is Tim Fletcher, and today I'm going to talk to you about the fundamentals of stormwater management for waterway health. I work at the University of Melbourne as part of the Melbourne Waterway Research Practice Partnership. So why does stormwater management matter? Well, Melbourne Water has two primary responsibilities relating to stormwater: managing of flood risks or reducing of flood risk, and also as the custodian of waterway health. And you'll probably see that list and think, oh, there's a little error there. They should be number one and number two. But in fact, that's deliberate, because both of these responsibilities are equal in the eyes of the law, in the eyes of Melbourne Water's management responsibilities. And so we need to manage these together. So today we're going to try to understand how stormwater impacts waterways, and then think about, well, given that, how should we manage it to maximise the potential health of receiving waters? And so here our focus is on waterway health, but this doesn't mean we suddenly don't care about flooding anymore. And indeed, the approaches to stormwater management that we talk about here have benefits in terms of reducing flood risk as well. But yeah, flooding is perhaps for another day. We can chat about that another time. So let's start at the start. When we have precipitation, which typically in this part of the world is rainfall, but could be fog, could be snow, if we were able to go somewhere to see that. In a natural situation where we've got a forest canopy or something like that, a lot of that water will be intercepted actually by the canopy, but some of it will make it through to the ground surface. Some of that water will be lost as initial loss, so taken up on the ground surface. But we might also get surface runoff. In an urban situation, of course, this changes dramatically, where we'll get a lot of surface runoff because we've got a lot of hard surfaces. And then we'll get runoff into channels as well, etc. Water that doesn't run off will infiltrate into the soil. Most of that will actually end going back up as evapotranspiration through plants or just through the soil surface. Some of it will form what's called interflow, where it's travelling at a shallow depth across the land surface. sort of at the bottom of the A horizon, and sort of travelling down towards waterway. And then some of that water will make it all the way through to the deep water table. Some of that might come back up as capillary rise as well. So this process, the important thing about this kind of complex process is that very little of the water in the natural situation ends up as surface runoff. Most of it is absorbed into the surface and then evapotranspired. In southeastern Australia, typically 80 to 90% would be evapotranspired. So little of it actually makes it into the waterway. Urbanisation utterly changes this story. We create all of these hard surfaces that produce runoff. That runoff happens very quickly. Water flowing through the natural surface on this natural side might not get into the waterway for days, weeks, months, years, even decades. Whereas in a situation where we've got constructed pipes and channels, etc., that flow will typically happen in the order of minutes. And the gross volume of water increases enormously because we lose a lot of that evapotranspiration, because that water is not soaking into the soil surface, but instead flowing across the top and then into pipes. There isn't that opportunity for trees, even if they are present, to be taken up, water to be taken up by those trees. And so we end up with a much smaller amount of evapotranspiration, evaporation and transpiration, and therefore a much larger amount of runoff. If we were to characterise the, I say here, the current approach to stormwater management, but to be fair, I think it's more the past approach. We've seen very big changes in recent years, but that past approach was characterised by just trying to get rid of water as quickly as possible. So we, in the situation here, we put it into a pipe through this pit. So it runs down the gutter, into the pit, into a pipe, and then we discharge it into a waterway. These two photos are actually, this is exactly what happens. So that pit flows directly into that pipe, and you can see that that waterway, which in this case is Little Streambuck Creek out in Mount Evelyn, is highly degraded and eroded by that huge volume of rapidly flowing water. And so we see really big impacts on the hydrology, on the flow regime of these waterways. On the left here we have, so we have two waterways here, both the same period, both with approximately the same climate. They're very close to each other. On the left side, we've got Yolinda Creek, which is almost entirely natural catchment. And on the right side, we've got Brushy Creek, which is a typical kind of outer urban. And you know two things. One, the really sharp and large peak flows caused by stormwater runoff, but also the relative lack of base flow over on this urban side. There's very little flow when it's not raining. We don't have that nice sustained base flow to provide habitat for the organisms that live in the waterway. And so our flow regime is utterly changed. The peaks changes, we talked about the base flow changes, the dry flow spells or the dry spells change, everything changes. Water quality also changes, and that changes for two reasons. The first is we have sources of pollutants that are much increased. So we've got zinc roofs, or we've got dogs defecating, or we've got metal being rubbed off car brakes, or we've got paint being spilled, or etc., kebabs being dropped in the street. But we also now have a very efficient mechanism to deliver water. If I was walking through the bush and I dropped a kebab full of chili sauce, none of that would make it into a waterway unless I happened to be crossing the creek when I dropped it, because that basically would be trapped on the ground surface, degraded there and then. Some unknowing possum would come and eats the chili sauce I just dropped. Whereas in an urban situation where we've got these hydraulically efficient gutters and then pipes, the next flow will wash that kebab down the street. It's not a very nice thing to think of a wet soaking kebab running down the gutter, to be honest. Anyway, that kebab would run down the gutter into the pit, into the pipe, and end up straight in the waterway, and all the pollutants that come with it delivered. And so the same happens for all those heavy metals, phosphorus, all the typical sort of pollutants. And so we see that there is a very strong correlation between the amount of impervious area. So in this little plot here that comes from a paper by Hatt et al., Belinda Hatt et al., we see a strong relationship between connection, which is in this case the percentage of the catchment that's made up of connected impervious areas. And then on the y-axis, the pollutant concentrations, in this case, filterable reactive phosphorus, so dissolved phosphorus essentially, and then total phosphorus on the right. So both of them are increased when we have more imperviousness. So urban areas generate and transport more pollutants into our waterways, which we kind of knew. So how can we manage that? Well, I suppose one thing we can do is try to reduce the sources of pollutants, but that's fairly hard. So for example, I could insist everyone takes off their zinc roof and puts, a Colorbond roof on, or I could use street sweepers every day to try to pick up brake dust that gets rubbed off cars. Although, to be honest, I'm going to struggle. So I can do some things. I can implement some policies to stop some industrial emissions. I can ensure that people aren't illegally discharging into the street. But there's a lot of pollutant sources, diffuse pollutant sources, that I'm not really going to be able to do much about. That's the reality of it. But I can feasibly reduce the delivery efficiency. So I can use stormwater control measures, we'll talk about those later, to reduce concentration, so to treat water to reduce the concentration, to reduce the overall volume of water, and to increase infiltration, evaporation, and use. Stormwater also impacts the channel form and the channel habitats. That big increase in flow, it's going to have a consequence, isn't it? It's going to basically wash away that channel substrate. But we also typically see a decrease in coarse sediment supply as we put in place a whole lot of sealing of surfaces, etc. We tend not to have much coarse sediment, and that coarse sediment, the supply of that is actually important for reducing erosion. It's that coarse sediment that takes energy out of the water in being transported. Without that, we tend to get increased erosion. And so we typically see this kind of process where our channels will start to deepen and widen as the level of urban land use increases. And so we go from a situation like this where we've got a small channel with very clean water to one here where we've got a much enlarged channel, and indeed we've had to use armouring to try to protect that channel. And we've, in all of that erosion that we've created, we then generate a whole lot of fine sediment that sits in that waterway and reduces the water clarity, and therefore reduces what can live in there. And so we see this real incision of natural channels. If we look at a whole range of geomorphic metrics or channel kind of form metrics, such as the presence of bars and banks, or the instability of the banks, or the amount of woody debris that there are, we see a really strong relationship with imperviousness. So impervious areas, which are essentially a good metric of stormwater runoff. The more impervious areas I've got that are connected into my stormwater network, as in drain into that network, the more flow change I'm going to have, the more water quality change I'm going to have. If I've got that flow change, I'm going to be washing away my banks and bars. I'm going to be causing bank instability as I start to cut down into the channel. And I'm going to be washing out woody debris so that I'm going to lose that habitat. And here we see a really, what we call a non-linear relationship, as in it's drops away really steeply and then starts to settle. So in other words, a lot of the damage is done by the time we get to, you know, even 2% of the catchment being made up of connected impervious areas. So we see here that by the time you get to, say, 5%, pretty much any damage you're going to get has happened already. So you don't actually need much impervious area before you start getting big effects. Even at, you know, 0.5%, you're starting to get big effects. Why is that? Well, we saw before that for each kind of square metre of impervious area, we're changing the amount of flow by perhaps, you know, 4 or 5 times compared to what was naturally there. So it doesn't take long before we have a really big impact on the total flow going down our channel. So what's the end result of this? Our flow regime's changed, our water quality's changed, our channel form, our habitat is changed. And it's no surprise then we end up with this complex kind of list of changes that all then have consequences on each other. This is a diagram put together by Chris Walsh and colleagues in 2005 in a paper that coined this term, the urban stream syndrome, meaning that urban streams are kind of ubiquitously degraded. And if we look here at this horrendogram, as Chris himself calls it, we see a real complex interaction of all of these factors. So flow changes, which affects water quality. Certain biota will be affected by that. That change in the water quality will change sediment in the water, which will affect light. That'll affect, etc. It just goes on and on. So in other words, as soon as you are allowing this stormwater runoff to degrade waterway, it's like a domino where it propagates all of these changes that are going to be pretty hard to undo. So what are some of the underpinning principles we can try to kind of keep in order to avoid having those impacts? This comes from a paper put together again led by Chris Walsh, but with a few colleagues from the University of Melbourne's Waterway Ecosystem Research Group, where I come from, so Matthew Burns and myself, as well as Chris, and then a whole lot of colleagues from other parts of the world, such as Derek Booth from Seattle, and so other people with kind of expertise in the same general area. And so we all got together and developed this set of principles for managing stormwater to protect stream ecosystems. Well, the first is we need to know something about the stream ecosystem we're trying to protect, and we need to set appropriate ecological condition targets for it. Now, most of us, that's not our job. We get given those targets. In Victoria, that's typically set by the State Environment Protection Policy, and Melbourne Water itself has targets about different waterways and what it wants to achieve. And those targets need to pay attention to what sort of waterway it is, what it's sensitive to. For example, a small headwater stream is going to be very, very sensitive to changes in flow, whereas a big estuary is going to be a bit more buffered against those impacts. The next important principle is to try to mimic the pre-development water balance. Remember before I showed that plot where I said, you know, typically in a natural catchment in southeastern part of Australia, we might get about 80 to 85% of the mean annual rainfall evapotranspired back up into the atmosphere. And that drops to about maybe 10% in an urban situation. So about 90%, you know, might be ending up as runoff. And so that's captured by this plot here, showing this is the sort of natural range of runoff coefficient. So the amount of flow that becomes amount of rainfall that becomes runoff in a natural situation. And this is what it looks like in an urban situation. So basically we want to bring that volume back to where it was before. So we need to reduce a lot of this water, harvest it, or do things to promote its evapotranspiration so it doesn't end up in the waterway. won't talk much about that today, but there's a great opportunity there, isn't there? That here's all this excess water that we could actually use as a resource, and at the same time protect our waterways. It feels like a bit of a no-brainer, doesn't it, to create that resource and also protect our waterways from that excess. The third principle, which is in some ways similar, but fleshing this out a bit more, is design stormwater control measures, SCMs, to deliver flow in a quality and a flow regime that mimic the pre-development processes, both for high flow and low flow. So we might, for example, use things such as rain gardens or bioretention systems, I'll talk about those later, to treat the water, and then use a combination of things such as rainwater tanks or infiltration systems to both reduce the overall flow, but also put a bit of water back into the urban landscape to try to ensure that it's we're recharging that groundwater the way we traditionally would have, or naturally would have. When we're judging our performance, we want to try to reduce untreated runoff in all but rare storms, because that's what naturally would have happened. So typically in this part of the world, southeastern Australia, we typically wouldn't get runoff across a whole catchment more than a few times a year, perhaps 10 at the absolute most, probably a fair bit less. And we want to do that in the natural situation. So for example, we could design a system such as an infiltration system, or a stormwater harvesting system, or rainwater harvesting system. And we could do some modelling in any of the commonly available modelling tools for stormwater, like Music, the one that's commonly used and that Melbourne Water uses, to see, well, how often does it overflow? So how often does it produce runoff that goes back into the stormwater network? And so this is an example of a rain garden that my colleagues and I, Darren Boss and Matt Burns and Chris Walsh, and quite a few colleagues and I built out at Mount Evelyn. And we measured that for a while and saw that it was overflowing perhaps only once or twice a year, and most of the time it was just infiltrating water into the landscape. All right, the fifth principle is to apply stormwater control measures to all impervious surfaces in the catchment. Now that might seem really ambitious, and we'll talk about that in a minute. But you'll remember I talked before about how you only need a very small amount of impervious area in a catchment contributing to the outlet before we get a really big change in the flow regime, really big change. And so we really need to try to treat all impervious surfaces so that we don't get that effect. As I described, it's a very non-linear effect. You only need a small amount of impervious area before you get a big impact. And this has been shown all around the world. On the left are some plots from a study in the US using a whole lot of catchments, and they showed the impervious area and then the loss of sensitive organisms. And then these plots I showed before on geomorphic characteristics such as bars and benches, bank instability, wood count, etc. So we want to try to, in a greenfield situation, design that greenfield so that all impervious surfaces, the runoff from all of those is captured and dealt with appropriately using the targets we've talked about before. Of course, in a retrofit situation, this is much harder. We need to be honest with ourselves about that. We're not going to do that overnight. It won't happen overnight, but it will happen. It'll happen by suitable planning that takes place over decades to slowly take the opportunities. Each time a road gets dug up, because roads get dug up regularly, we take the opportunity to implement some new things. Each time there's an opportunity, we take that opportunity. All right, so what are some of the treatment processes that we can use? And I use treatment here carefully because we're not talking about just water quality treatment. We're also talking about managing the flow regime and providing a water resource, for example, through harvesting. So I mean treatment in this very sort of generic way. Well, the first one that's commonly used is detention. Flood retarding basins or detention basins use this. Wetlands use this, where you basically take in a big peak of flow and then you store it and release it out at a lower rate. So it's what I might call the bathtub effect, where you might have, for example, a really high flow tap going into the bath. You know, maybe let's pretend it's a fire hose filling up the bath in seconds, but we've then got a plug hole that's letting that bath go slowly down over, you know, half an hour. So the flow rate going in is really sharp. The flow rate going out is lower. We tend to do that for flood control so that we can avoid downstream infrastructure such as culverts or bridges getting submerged. And we also do it in things like wetlands because it has water quality benefits, allowing that water to sit and think about itself for a while. So to sit for a while allows sediments to drop out, allows biological processes to start to occur, so we get water quality treatment. And so it might seem like a good idea, and it probably is, but there's a bit of a catch too, because if we detain the water so that the flow rate drops from here to here, that's good, except if the threshold above which we start getting erosion of the channel is all the way down here, what we've actually done, as you'll see on my plot, is we've increased the total amount of time when my flow is sitting above that threshold of disturbance. And in that situation, we can actually get an effect where we have greater erosion impact than we had previously, because we've increased the total time, and so more work is done on the channel. Storage and harvesting. This is where we capture rainwater or stormwater from impervious surfaces to provide water for human uses. Might be irrigation, toilet flushing, laundry, hot water, or in many situations we might go through to the whole way, providing treatment using appropriate filtration and then UV disinfection, for example. And that can be done in a whole range of ways. We can use that water then to provide you know, irrigation to keep the urban landscape green, etc. Infiltration is another method we use, where we intercept water, infiltrate it into the landscape, try to recharge groundwater and contribute to base flows, and also try to provide some water for nearby vegetation. Evapotranspiration, where we, it's often combined with infiltration, where we put water into a basin and have a lot of vegetation that then is using that water. Or we might actually take harvested water and apply it to the landscape and promote evapotranspiration that way. This is a way of reducing the overall flow volume. So we're trying to you know, mimic the natural flow regime using evapotranspiration as one of our tools. Here we now start to talk about some of the water quality processes. So sedimentation, typically combined with detention. So we store water in for a period of time, and we get that water sitting still enough for sediment to drop out of that water. Or we might use more sophisticated physical and chemical filtration. Here we've got systems where you've got a permeable pavement, and then under that you've got some granular filtration media, similar type of system here under this permeable pavement here. And then through to sophisticated biological treatment processes, such as you see in constructed stormwater wetlands or bioretention systems, often called rain gardens, where we're relying on plants and microbial communities to do a lot of the treatment for us. So what sort of technologies can we use then? Might we think about using to put these principles and these treatment processes in place? Well, let's start with the ones that, from my point of view, are least interesting and perhaps least useful. So the simple gross pollutant traps, so necessary. I'm not arguing they're not necessary or useful in certain situations, but they're not very multi-purpose. They essentially just remove coarse pollutants They don't really provide any biological treatment, although lots of the manufacturers try to claim lots of advantages. But they are really important and effective as upstream pre-treatment because you don't want, for example, if you build a wetland, you don't want it to fill with litter. It won't be good from a treatment performance, but it also won't be socially sustainable. It's important to note that these provide no benefits from a flow regime point of view. They literally are just a pass-through, treating the water and then it's discharged. The next step up is probably the sand filters, so aiming for a little bit more fine treatment, but again, no flow regime benefits, no evapotranspiration benefits really, but are quite useful where, for example, you want to regularly change the filtration media because the water is highly contaminated, for example, so you wouldn't want a vegetated system. Rainwater or stormwater harvesting. So this is where we collect water and then use it for purposes. For this to be effective as a stormwater control measure, we need to make sure there's a regular use of that water, because there's not going to be much use in our tank as a stormwater control measure if it's full. Rain will come into the tank and basically just overflow. So we need to make sure we've got water being drawn out of that system regularly. In some cases, we can combine it with passive irrigation. So we might have a trickle release to supply water to nearby garden area or green open space. And we increasingly see much more sophisticated designs of these where we have a controlled outlet that will release water for passive irrigation, will release water for base flow, and will also release water prior to a big storm based on a connection to the Bureau of Meteorology's digital forecast system called Australian Digital Forecast Database, which releases new forecasts every 12 hours. So these systems called Tank Talk can connect to that and automatically say, oh, I predict my tank is going to overflow tomorrow because there's 27 millimetres of rain forecast and I've only got room to store 11 millimetres. So I know I need to release 16 millimetres between now and then. And so we're increasingly seeing that type of technology being used and being available. As I say, we can have this passive irrigation system where we release some of that water to provide garden watering. Ponds and sediment basins. So as you'd expect, these are essentially about sedimentation, promoting sedimentation, but also with a little bit of vegetation, a little bit of detention. So, you know, some benefits. They tend to be used upstream of wetlands very commonly. Wetlands are a very flexible and typically aesthetically appealing system, offer good detention. Sometimes we can see storage and harvesting being taken from them. Good for sedimentation, filtration. Generally really aesthetically appealing. They're pretty popular in land development world, where developers will use them as a sort of recreational and amenity asset, as well as meeting their stormwater management responsibilities. Next on the list, we have our rain gardens and bioretention systems. These are systems that are really flexible, designed to kind of look like a garden, receive stormwater, promote very effective biological treatment processes using the plants and the microbial community. Very flexible in terms of what they look like, where they can be placed, etc. And where they're unlined, they can be really effective in promoting some exfiltration so that we get a little bit of groundwater recharge as well. And you'll see here just a few examples of systems that, you know, with quite different looks, and you see them in very dense inner city situations as well. One of the simplest systems are the swales or the buffer strips, where basically instead of conveying water in a pipe, you use a swale drain type system. They actually provide a bit of infiltration, some sedimentation and filtration, a little bit of biological treatment, not particularly strong, but a little bit. They have the benefits of some detention, good treatment, some infiltration, but they also serve a conveyance function. So they can, in many situations, save money, because at least for part of the drainage network, I don't actually need a pipe system. And myself, in a number of jobs, I've ended up, the client has not been particularly interested in doing stormwater well, but when they've seen the cost savings available to them by using these systems, all of a sudden they become interested. They tend to work fairly well at slopes between about 1% and 4%. Less than 1% and you have issues of draining them, although they can be solved with putting an under drain or something like that. And greater than 4%, you need things like check dams to stop there being erosion. One of my favourite systems are the infiltration systems. In part, I like them because, one, they're mimicking that natural process of getting water back into the soil, back into the ground. But they also can be hidden afterwards. So on the top here, we see a picture of a system being constructed on my own property, actually, which was then planted up into a garden. And to this day, you basically can't tell there's an infiltration system there. It's basically just a big garden with lots of trees that are using that water. And the same here on the bottom one, we have a sort of infiltration basin that, when water is not in it, it basically just sits as a nice bit of green landscape and can provide recreational benefits. And we have a whole range of other green infrastructure, such as green roofs, green walls, and all of these are starting to provide a whole range of benefits to people in terms of aesthetics, but also good evapotranspiration and biological treatment benefits. And so we start to see a whole suite of tools available to ensure that when we urbanise our areas, we can, even though by definition we have to create a whole lot of impervious surfaces and constructed systems, houses, buildings, footpaths, roads, etc., we can use these kind of more natural elements, wetlands, swales, infiltration systems, rainwater harvesting, stormwater harvesting, systems to mimic the natural flow regime, mimic the natural water quality process, and to reduce the flows going into our waterways back towards the natural level, particularly to get rid of some of these peaks, and to restore some of these dry weather periods by providing some infiltration and base flow, so that we avoid having big impacts on our waterways. The arguments for doing so are, however, multiple. So sure, we protect our waterways, and that's an important thing. That's part of our charter at Melbourne Water. We're the custodian of waterway health, so that's our job. But we also create much nicer urban landscapes. We've got landscapes with trees, with green elements in them, with good moisture availability for vegetation. We've got a water resource provided to us by either rainwater harvesting or stormwater harvesting, rainwater being off the roof, stormwater being all impervious surfaces, roads, roofs, etc. And perhaps ironically, by reducing this runoff coefficient by all of these measures, we reduce the risk of flooding, and we make the management of flooding downstream a smaller task. And so whilst we set out to reduce flooding in 30, 40 years ago by managing stormwater using pipes and channels, etc., ironically what we do is, we do reduce the flood risk to us here where we are, but we transfer that risk downstream. And some of the most terrible floods, both nationally and internationally, in the last 10 years have been really sad reminders of that, I suppose. And so here we have a chance to have better waterways, better urban landscapes, and reduce flooding. What's not to love? Thanks a lot. I hope you've enjoyed my discussion. I would be very happy to chat to you at any time. I've been working around with Melbourne Water for quite a few years now. It's a bit depressing. Anyway, and I'm always very keen to chat. So either hit me up with an email or even give me a ring. Okay, have a great day.